Good morning, Algebra 2. Today is the second video dealing with section 14-1. And I have something in front of us because I realized that I made a mistake in the first video. I'm certain some of you probably heard it, caught the attention. So section 14-1, we are fitting exponential functions to data. And again, this is your exponential function. And I made a little bit of an error, or I don't know what I was thinking, but I just wasn't thinking probably. So, and I didn't want to start all over with a new video. So if I make a mistake, I'm just going to keep going. So, and I found my mistake is this is an exponential function. Again, when we did the ratios of the functional values, we found what b was. And I made an error of saying, well, if b is greater than 0, that will make it a growth function. Well, I made a major mistake. That should have been b is greater than 1. We'll make it a growth function. But I was correct on the other one. But between 0 and 1, this will be a decay function. So I am so sorry for confusing you if you got it on the first video. So again, the b here, for it to be a growth function, an exponential growth function, b has got to be greater than 0. For it to be a decay function, it's going to be between 0 and 1. All right, now I've given you some time to think about the beginning part of section 14-1, and we looked at 4 sets of data in the Explorer part, and we got a good idea of what to look for exponential functions, what to look for linear functions or quadratic functions, which is really going to be more important in section 14-2, but I just thought I'd just show it to you guys. What we're going to do today is the second video is we're going to do everything. We're going to do examples algebraically, and then I'm going to show you how to do it graphically, okay? So, section 14-2 is in order for us to do explain 1 and explain 2. Well, explain 1 is doing it the algebraic way. Explain 2 is doing it by your graphing calculator. So what I'm going to do is I'm going to take the examples of explain 1, I'm going to do them algebraically, and then I'm going to do them graphically. So the first thing we're going to run across here is I do hope you guys read your book, because again, you got to read math books, you got to read your science book, you got to read every book you're given just to get an idea of what the teacher's talking about or what the subject's about. But the one thing I want to draw your attention to is the very last sentence on page 704. It says, in the real world, sets of data rarely fit a model perfectly. Now again, if you went back to look at the Explorer, all that data was just fit perfectly, okay? We've got the common ratio to be the same, but sometimes we're not going to get that. But if the ratios are approximately equal, an exponential function can still be a good model, okay? So when we did A and D, again, we were able to see the ratios were the same, but the data we're going to run across is sometimes our ratios are not going to be the same. So we have to do what is a rough approximation, okay? Still ties into the same rules from the Explorer, okay? All right, so explain 1. The only way to do this is by example. So here is example 1. And once again, we are trying to create our function. And our goal to create this function is we need to find out what b is and we need to find out what a is. Now you're probably saying, what's the big deal with all this? Well, statisticians, probably said that wrong, people who study statistics have all this data set up, and if you look at this first one right here, they're just looking at data from 1790 to 1890. And based upon this data and from this information, they could create a function where we can figure out what the total population is in 1900 or 1910 or 1920. So this is what statisticians do. Specifically also actuaries do this. And again, if we create our function here, we can get a good estimate of what will happen in the future or what might have happened in the past. So again, a lot of stuff has a lot of importance, okay? So doing this here, here's our set of data. The first column is your x's. The second column is your functional values or your y values. So one way to estimate the growth factor, again, do we know that this is a exponential growth or is this an exponential decay? Once again, if you look at your data here, all these numbers are increasing. So this tells me my exponential function here is a growth, okay? So we have to find the b. And to find this, we got to go and find the population ratios from decade to decade and do an average of them. Now, like I said, this is the algebra part, and it's really simple. So again, 1.35. If you look at this first one right here, how did they get 1.35? Well, they just went up here using our calculator. They took 5,308,483 and divided by 3,929,214. And they got 1.3510. And what they did is they just took that data, that ratio, and just rounded it to the nearest hundredth. Okay? They went all the way down. So right here, 1.35 is this part. And then 1.36 is this ratio. And 1.33 is this ratio. So they do all that, find all those ratios, and then we have to do a average of this, because you're going to notice that all these ratios are not the same, but they're really close to each other. So again, since they're really close to each other, we know that this is going to be an exponential function. You with me? All right, so they found all these values. As a matter of fact, they found 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ratios. Again, if you don't see that, here's your first one, there's your second, there's your third, fourth, all the way down to the 10th. Oh, excuse me here, I'm writing down, saying 10 and writing down 10, all the way down to the 10th, and that's why they divided by 10. This is the algebraic part. So you take all this value and round it up. They went and roughed it up to 1.32. And this part right here is your b. Oops, lowercase b, Vince. Okay, is your b. So we have found that our common ratio, or our value b, is 1.32. So that is a rough estimate. Okay, it's just an average. And you're probably saying, where do they get this 3.93? Well, again, remember, this is your b. Let's use a different color so it stands out. This is your b. And guess what this is? If we go back and think about sequences and the formula for sequences, this is the first term of your sequence. So this is a sub 1. And what they did is, this right here is your first term of your sequence. And what they did is they just took this right here and made it into a decimal, 3.93. You can do that. Again, I don't think you want to put 3,929,214 right here. You can, you'll get a more accurate reading, but we're just going to round it up to the nearest hundredth. So this part right here is an approximate model of your function. The bottom part here is doing it graphically, which I am not going to hold you guys responsible for doing this. Okay, graphing it, we'll let your calculator do it. Okay, now I just showed you this part right up here. This is the algebraic way. This one takes a little bit of time. But what I want to do now is go and apply this from Explain 2 by using our graphing calculator. Okay, now again, let you guys know this was done. We've done this type of stuff before, and you're going to have no problem doing this. All right, we did this before. So what we're going to do is we're going to take this set of data and we're going to make a scatter plot and make a regression from it. You with me? All right. So make sure everything's on the screen. So what we do is you take your calculator, click on Stat. You with me? Edit. And once again, I did this an older one. L1 is going to be your first column here. This is L1. Now what I want to do is, instead of doing it 1790, 1800, what we're going to do is, if you look at your chart here, we're letting x become 0. So that means in our L1, we're going to let these become 0, 1, 2. You with me? So I'm going to take all those here. We're going to say, well, we're going to let 1790 mean start off with our 0. Okay? So we take our problem in our first row. L1 is going to be 0, 1. You type your numbers in and hit enter and go all the way down till 10. Oops. Not paying attention. Saying 10 and writing down, typing in 10. So this is all your L1s. Okay. Now we go to L2. Now L2, we are more than welcome to type these whole numbers up, but what I'm going to do is I'm going to go and put them in decimal representation. So 3.93. I'm just going to round them to the nearest hundredth. 5.31. 7.24. 9.64. That's hopefully my bifocals will catch on. 12.86. 17.06. 23.19. 31.44. 38.56. 50.19. 62.98. So we have listed all our data in our calculator. All right. Okay, are we ready? The next thing we do is we go to y equals. If you have any data in there, clear it. You'll go up to where it says plot 1. You want to highlight that. In other words, it's got to be highlighted. It's highlighted. Plot 1 is highlighted. Okay. Okay, now what we want to do next is we want to go to graph. And at the same time, to see our data, we're going to hit zoom. And we're going to hit zoom stat. All right, now this is just taking all our data and plugged into our function. Now when we get to section 14-2, we're just going to be looking at our set of data, and we got to ask ourselves, is this linear, is this quadratic, or is this exponential? All right, now based upon the way this one looks, it does look quadratic, but the one thing we need to see is here our values are really increasing quickly, really are increasing from each term, from each y value to a next y value. So this is going to make it an exponential function. Okay, you with me? All right, that's what this looks like graphically. That's what this part is right here. Now, in the diagram here, you see this line right here? Where I'm not going to hold you guys responsible. This is what we call a best fit. So in other words, your calculator can do a best fit of this, but I am not going to really focus on that. All I'm focusing on is how to get this function right here. All right, so the next thing we do, okay, we'll quit out of this. We have all our data in there. We want to go to stat. While we're in stat, we want to go to calc. And we've already said that this is a exponential. So again, down here, there are a few buttons that we're going to have to deal with later on. There's linear, there's quadratic, there's cubic, there's quartic. But what we want to look at is, in this case, is the one that says EXP REG. That's a exponential regression. So we hit enter. Now again, I don't know, some of you guys have different calculators than me. But you'll have to maybe go to YouTube and figure that out, okay? So again, we know that this is an exponential. Again, we have list 1 and list 2 set up. All we need to do now is go all the way down to where it says calculate and hit enter. And there is your problem. Now again, this one is going to be a little bit more accurate than what we did. Okay. Again, if you look at the problem here, this one tells us that our B is 1.323 and our A is 4.11. Again, the calculator is doing a little bit different, it's probably giving us a better, more accurate value than here. So again, they're very close to each other. So this is how you would do it by using your calculator, and this is the way you would do it by algebraically. Now again, the biggest discrepancy that we're going to run across is we see that A sub 1 is 3.93, and in our calculator it shows us that our A is 4.12. Again, I can't explain that. We just have to accept that. Maybe I typed it in wrong, but again, they're relatively close to each other. Now, with that said and done, we can if we go back to this function right here, we can figure out what our population is in the year 1900. So again, in your calculator here, all we got to do is everywhere you see an X, you let it become 11. So that will give you an estimate of the total population. All right, so that is example 1. All right, now example 1B is the same thing. I'm going to let you guys try that. Oh, no, I'm going to do that. Let's do that together, and then I'm going to go back and do another example. First things first here is they found us that our A is 95.3. We have to find an estimate of B, so we have to do a ratio. Remember, this is the algebra part, so we have to go 55.9 divided by 95.3, and they got 0.59. Again, they round it to the nearest hundredth. So I did all the work for us already. And then you're going to notice that the ratios in this case, there are going to be 9 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you add up your numerator and divide everything by 9. So we get a rough ratio of 0.58. So this gives us an approximate model. We can find a more accurate model if we use our calculator. And I'm going to say that for the next one, okay? This is the algebraic way. So when you read your directions, when they say an approximate model, go ahead and do the algebraic way. All right, now let's look at number 5. And we're going to do this one by the calculator. Fisheries. The total catch in tons for Iceland's fisheries from the year 2002 to 2010 is shown in the table. So again, this is in millions of tons. They took our values and they put it as a decimal. You're more than welcome to. They did theirs into the thousandth. You'll be able to do it this way or the other way, tenths, hundredths, thousandths, whatever. The more digits you have, the more accurate your answer is. Again, this is your years, starting with 2002 up to 2010. Again, we see that I'm going to go and let x become 0. Again, I am not worried about the graphing part, okay? Right off the bat, this is our function. Now, if you notice here, okay, all our y values are decreasing. So that tells me this is a decay function. So my value of b will have to be between 0 and 1. All right. Now you're more than welcome to do this the estimate way, the algebraic way. You're more than welcome to, but I'm going to use this one for the calculator. All right. So here's how we'll do it. Clear our screen. Go to Stat, Edit, clear our lists. And then we're going in the L1 is going from 0 up to 8. Once again, we've done this before, so this should be relatively new for you guys. If you don't have a graphing calculator, guys, you're going to have to do it algebraically. All right, so L1, we put in 0 through 8. All right, so L2 is we just type in our values. Again, I'm not talking here, but it's because I'm just typing everything in so I don't make a mistake. See, I made a mistake. It happens. There's our data. We can now go ahead and do, we've already got plot 1 highlighted. All we got to do now is go to zoom, zoom stat. There it is. There's the graph of that. Again, it's a decay function because it's going down. It almost looks linear, but it's not. Okay, that's the hard part. When we get into seeing the differences between the two. Remember now, if these common ratios are all the same, again, it's going to be exponential, but it also could be, well, hang on to that. We'll just worry about that when the next section comes. All right, ready? So the next thing we do now, we can figure out what this function is. We know A is 2.145. That's a rough estimate. Let me show you based upon our data, what the answer is. So we go to stat, go over to calc. Okay, we find the one that says EXP regression. That means exponential regression. You go on and click that, and you go all the way down to evaluate. There we go. Again, like I said, this one, based upon our data, is going to be a little bit different. Okay, we can figure out what our B value is here. Now the calculator, again, is going to give us a different answer. It's going to be a little bit more accurate. 2.119 times, again, B is 0.917. And there is your exponential function using the calculator. Now remember now, over here it's going to be a little bit different. It's going to be a whole lot different because we're doing approximation. Again, if I go back to the page, what page is that on? 707. What they have here in their solutions manual, they got the B to be approximately 0.92 by doing it. So again, this is the approximate. This is the algebraic way. It's going to be y equals 2.145 times 0.92 raised to the x. So again, this is the rough estimate or the approximate using the ratios here and average of the ratios. This one is by using our calculator. All right, now I hope you found this to be very applicable. You may have to go back and watch this video again. The key is using your calculator, but also try to do it by the average ratios, and you'll probably get too similar, well, closely similar. Okay, again, both of these are okay. They're approximate exponential model. We can use either of these two to figure out. Well, we can easily find out what the total catch will be in 2011 by letting x become 9. All right. Okay, I'm going to stop here. This is the second video. Again, sorry for the mistake on the last video. You probably I filled that into you guys. All right, guys. Catch you later, man. Bye.